For me, it just said recording has started. I don't know if it said that for you guys too, but yeah, okay. So I did start recording now, so hopefully it's working, and then I'll put this up later. Um, so yeah, I have the worksheet here. I can like copy and paste screenshots from the worksheet into the drawing program. There we go. And that way we're able to do the problems. But I'll start off like normal, so we'll do a little bit of review of the stuff that you learned, hopefully by watching the recorded lectures, and from there we'll go on and do the worksheets. So for now, how about we do review? Um, so we'll start with chapter 20, okay, which was carboxylic acids. If at any point, like, my handwriting sucks or the quality is bad or something is too small, definitely let me know. That's like the really helpful type of feedback that I can definitely use. If you want me to like scroll up or something, then also let me know. Okay. But the most recent, or so, the first chapter you learned this week was carboxylic acids. Before then, you had amines and everything. So there's a few questions that are reviews of what you learned about amines, but let's go through the new stuff, the carboxylic acids. Okay. And the fortunate thing that you might have noticed is that most of this is already review. You've seen a lot of this. Okay. So the good news here is that you've gone through the harder part of the course, right? I could tell you, at least in my experience when I was taking the course, and from the impression that I've gotten from a lot of other people, is that chapters 19 through 6 or 16 through 19 are the uphill, and then from there you're going back downhill. Okay, meaning you've seen a lot of the stuff before. It's not all very new, at least a little bit. So like this is 20 and 21. A lot of this you've seen. There's a couple new things, so don't like fully neglect chapters 20 to 21, but like it's they're not anywhere near as bad as the previous chapters. Um, there's a little bit of uphill with chapter 22, and then from there, chapters 23 and 24. When I took the course, at least, that was the sort of point where like it was the home stretch, and we were just getting through to the end. Not a lot of new reactions, mostly just applied organic chemistry, right? So this is like, at least with my experience when I was taking the class. And so right now we're at this part, which is really nice because like we've seen a whole bunch of this stuff before. A couple new things, but we've seen a lot of it. Okay, so let me get rid of this because I don't know, the professor might be watching. Okay, so for carboxylic acids, you started off by learning about synthesis, and there are 5 ways, I think, 5 of really synthesizing carboxylic acids that you learned. Okay, so one of them is oxidation, and you learned a million of these things. Okay, so let me try to be a little bit interactive, maybe. Does anybody want to tell me a way that you can oxidize something to be a carboxylic acid? There's 5 or 6 or something of them.
Dichromic acid.
Okay, yeah, so normally coming in the form of sodium dichromate, right? And acid? Yeah, I think so. Okay, that's one way. Um, Something else?
Potassium permanganate.
Yeah, potassium permanganate uh, is just generally a really strong oxidizing agent. Maybe there are some more. I guess this is going to carboxylic acids, and a lot of the other ones that you've learned, like Swern or DMP, only go to aldehydes. So for carboxylic acid, let's see, maybe there's 1 or 2 more.
Bleach with excess tempo.
Yeah, how about that? That's one. Okay. Yeah. Uh, is anyone able to think of another one? I'm not sure if I could. Yeah, let's call it there. Okay. Maybe there's another one or two, but we got some of the big ones. Okay. Second, uh, let's say you have a double bond, like, I don't know, some double bond, and you want to break it in half, you can make some carboxylic acids. Okay. So one way to do that is with potassium permanganate and heat. Okay. And that one we know makes two carboxylic acids. There's another way to do this though, where we cleave a double bond and wind up with two carboxylic acids. Okay? Does anybody want to let me know what that way is? Anyone? Okay, how about
Ozonolysis?
yeah, so you could do ozonolysis, right? But typically ozonolysis will be used to get you two aldehydes. But if you want to use ozonolysis to make two carboxylic acids, then what you could do is in the second step, instead of doing a reductive workup with dimethyl sulfide, you could use hydrogen peroxide. So this is an oxidative workup. Okay. So there's two options of how to cleave a double bond. Okay. Both fairly nice ways of getting this. In practice, you'd probably use the ozonolysis way preferably because heating things with concentrated potassium permanganate will probably mess up whatever else you have in your molecule. So ozonolysis will pretty selectively work on double bonds. That's kind of nice. All right. Let's see, what's another way? So let's say you have some phenyl ring with stuff like this. Well, it'll be the same sort of reaction, potassium permanganate and heat. And then all of those carbon things will come off and you'll just be left with your carboxylic acid hanging off. This will be like benzoic acid in general, okay? And then this is, kind of useful because you could have other substituents hanging off. You could, let's say, first do Friedel-Crafts to get this carbon-carbon chain on there. You can get other substituents para, ortho or para. And then you could do this. So now you have a withdrawing substituent with an ortho or para thing next to it. So that's kind of nice. So this is like you've seen this though. This is like old news, I guess, right? Okay. Two more ways. This one's new, I promise. This is not number 2, this is 4. So let's say you have like a Grignard reagent. And then you give it CO2, like gas. So from there you can get this guy to attack there. This will pop up, and then there you go. You just added a carbon and made it into a carboxylic acid. So I'm not sure how much you guys have seen this before. I think at some point in the past I've tried to mention this before, maybe to my people who took Orgo 1 with me. This is like something that maybe your professors in the past have tried to like throw you off with, but now you've actually learned it, so now it's like actually a fair game question, whereas earlier it was just a question that they would ask you that wasn't really fair game and, kind of rude of them. Okay, one last way, I think. So if you have like a nitrile, then you are able to do acidic cleavage of a nitrile, and then that will turn it into an acid. Nice. Okay. So these few sections will be are one of the main times that you're learning what you can do with nitriles, which is kind of good. Like that's one of the actual new things that you're learning in this section, is that you can do a bunch of chemistry with nitriles, which explains why earlier in Orgo 1 and earlier in this class, if there was a nitrile on a molecule, you had to be kind of sensitive about what you can actually do with it. But
I have
now
a question.
yeah,
Oh, sorry.
no, this is good. Thanks,
Uh,
thanks for asking.
in this fifth one here at the nitrile, do we have to know the mechanism for this? Like I can, or no?
So yeah, I was thinking about this earlier. The mechanism is in the book, I'm pretty
It's like
sure.
very repetitive, like a lot of like protonation, right? Like a few
Yeah.
protonations. Okay.
So let's see. This one, if I remember correctly, might have been something like you protonate there, okay, which will give you something like that, and then yeah, okay, yeah, it'll be a few protonations, right? Um, Now you get like some water that'll attack onto there, which will look like that, and then yeah, it should be probably something like this, and then you protonate the nitrogen again, you move the carbonyl, you move the electrons down to here, and so on. Um, I would say this is probably a good mechanism to know. From what I remember, it didn't really come up very much, but I could definitely see him asking about it. So, yeah, it's good to know. From what I remember, it wasn't like a big point in the course, though. Does that answer your question? Hopefully.
Yeah, thank you.
Okay. Yeah. Thank you for asking. Yeah. Okay. Um, so in that case, asking questions directly through the like just by unmuting yourself would probably work. I think that's completely fine and reasonable. Uh, there's like a fair amount of people in the call, but at the same time, like that's a kind of important question, and I imagine other people were asking too. Like Emily's asking in the chat now if this is the hydrolysis of nitriles, and yes, I think it is. That's what I would call it because you're breaking up a nitrile into an acid with the like with water with H3O plus. Um, yeah, there's okay, yeah, yeah. I would say this is the hydrolysis of nitriles. That's a good way to call it. Hopefully that's what the book specifically calls it, but I'm not sure. All right, let me get rid of this stuff and just write that like it's probably good to know the mechanism. Okay, cool. All right, so I think those are kind of the major ways to synthesize acids. So you have oxidation, you can cleave a double bond. Let me make different colors. So you can cleave a double bond like that. Um, if you have a carbon-carbon chain hanging off a phenyl ring, then you can remove that whole part and just make it into an acid. This one is new, and this one is new. Okay. Cool. Okay, and then you went on to do some reactions with them. And what's nice is that you probably already knew a lot of these. So I won't go through all of the reactions. I'll kind of just focus on the things that were important, and we'll be done with chapter 20 in like 5 minutes, which is kind of nice. Okay? So one reaction which you've seen covered probably like the fifth time now is Fischer esterification. Esterification. Okay, I think I spelled that right. For some reason on the whiteboards, my spelling tended to be pretty fine, but when I'm writing it on the computer, uh, all of a sudden spelling becomes a real challenge for me. So bear with me. Um, yeah, so here you know this is you take an acid and an alcohol, and then it's in equilibrium under acidic conditions, specifically acidic conditions. to make an ester. Okay? This is, at this point, needless to say, this is a mechanism that you should know. Okay? You've seen it a whole bunch. The mechanism for this is kind of like a specific case of the mechanism for a couple of other things. For example, in like chapter 21, you talk about transesterification, where you're taking an ester and swapping it out for another thing. It follows pretty much the same mechanism as this. So this is kind of a more specific case of something that's like broader, right? But you've seen that a whole bunch. That's kind of like a common thing that's been around for a while, right? Now, another thing that you can do is you could take an acid and diazomethane, and you can use it to make a methyl ester. Right? So to draw that out, what actually happens is you have your acid, you give it diazomethane, which is that, or maybe I'll actually draw out what diazomethane looks like. I guess it's not Me. Yeah, maybe I shouldn't write Me because it's actually a CH2, which is not a methyl group. So maybe I'll actually write out CH2. Okay? And then here it's CH2. And from there, you're able to get that, right? So this is nice. This is like a common reaction that you can do. And methyl esters are pretty common. So this is something that like people will do a lot. The weird thing is that like, great, but you knew how to make this, right? You can make this with Fischer esterification, which we just talked about. So this is like not really a revolutionary concept, but the reason you would do this is because this gives you like very, very good yields. Okay? Fischer esterification is in equilibrium. So your yields, you can expect to lose some of like, you don't expect 100% conversion all the way, right? You could do some stuff to kind of make it like help it go along, but this one will really work very well. So it'll give you high yields, and you know when you're working with in a synthesis lab, that's really what you want. So that's the reason that this is good. I'm not too sure about knowing the mechanism for this one. If you do need to know it, I've seen it show up in like the recitation from last year when I took the course. So I'll go through it kind of quickly. But it could be, I guess it could be good to know. All right, anyway, let me start actually going through it. So what you do is you have your acid, and then let me draw. Oh, oops, there should have been a double bond here. Sorry about that, guys. Then you put your diazomethane, right? And this minus charge is going to want to form a triple bond. So that's going to kick these electrons over to here. And you're going to pick up that hydrogen, right? And, well, you know, these electrons in this bond are going to move around and they'll go somewhere. Let's just say that they, like, move up to here, okay? And from there, so we've protonated this CH2, okay? Maybe this should now be an O minus, and here's our double bond. So now we have a CH3, and we have an N triple bond end hanging off of it, which, let's see, I think this is the one that Professor Smith likes to call the world's greatest leaving group, I think. Hopefully, at least I would say it probably is. So from there, we're able to just take, we're able to just kick off this leaving group with whatever on here is going to be the most nucleophilic. Okay, so this oxygen over here will do it. There we go, kicks that off. this minus will come down without a problem. And there you go. Okay. So that's it. It's one step. It's nice. Diazomethane is like super very reactive. The reason that a lot of people don't like to use it is because like it blows up. I imagine that Amos or Professor Smith talked about it a whole bunch in his recorded lecture. Well, yeah, it's fairly dangerous, but at the same time, like this is just such a clean reaction that a lot of people like to use it because it gives you such good yield, and this is like really a commonly wanted product. Methyl esters are really common, especially in nature. So this is kind of a common reaction. Okay. All right. That. Oh no. Okay. So I had a few more things to talk about for chapter 20. Right. So, we can also do some stuff with like, if we take an acid, then you can turn it into an alcohol. All right. These are reductions. And going from acid to an alcohol, well, you know how to do that. This is specifically a primary alcohol. You know how to do that. You just take lithium aluminum hydride and, really blast your acid with it until it becomes an alcohol. This is a super strong reagent, so this will happen pretty easily, right? But let's say that we want to go to an aldehyde. Well, this one you've seen before, although now you're relearning it, and now you are really supposed to know it for this chapter, is if you have an acid, this is like the least reactive possible thing. So going up in the reactivity series like that is kind of hard. What instead you'll do is take your acid, make it into an acid chloride, and then go to an aldehyde. And to do that, you have to use one of those special reducing agents. So in this case, I think it is lithium aluminum hydride O-tert butoxide, tri-tert butoxide, right? Yeah, there we go. Yeah, tri-tert butoxide, I think. So I'm pretty sure this is the one that you use in this case. It's one of the much more mild reducing agents. So this is kind of like one of the specific uses. Okay. There's a bunch of other ones of these. So like lithium aluminum tri-tert butoxyhydride is one. Sodium borocyanohydride is another one that you learned recently. Yeah, there's a whole list of them. This is just one of the particular cases that you should know. There's not a lot of good ways to really keep track of them besides just like remembering which reaction corresponds to which. There's not too many of the reactions, so just remembering them is really one of like the effective ways of keeping track of it. There's not a lot of real like big brain strategies to do it. Okay. All right, cool. So maybe an important point to note is that like now you've formally learned the reaction for going from acid to acid chloride, where you kind of had known it before because like you needed it to do a lot of stuff, but now you're learning it yet again, and you're really expected to know it. So to do the conversion here from acid to acid chloride, you use one of two things. So you can use either SOCl2, not SO2, there we go, SOCl2 is one option. And this should be catalyzed by pyrimidine. You need some sort of base, I believe. Yeah, that's right. Okay. Or the other option that you can use is oxalochloride. And here's a real bonus question for you guys. You've seen oxalochloride before. Where have you seen it? Anyone?
Swern.
There you go. Yeah. So you need it to do the Swern reaction, right? So now you're seeing it again, except I guess in Swern it was also a reagent, but yeah, now you're seeing it again here. So you can also use it. And well, I don't know how it'll be because the course is totally different now, but in the past, Professor Smith really loved to talk about this, and every single time he would give a lecture, he would say, oh, you could do it with SOCl2 or oxalochloride. You should know the mechanism for oxalochloride, or not know the mechanism, but like you should know about how you can use oxalochloride too. Okay. So I was looking up the mechanism earlier, and maybe there's a reason that I didn't remember it from when I took the class, which is that it's pretty complicated. Okay. So you have to use DMF, dimethylformamide, or whatever, to do it, and it involves the production of some kind of complicated reagent that like is an intermediate step. So I don't think the mechanism is something that you should know, or maybe there's an alternative mechanism that like you should know, but for the sake of the class, I think what you should know is what products you get as a result. Okay, so if you use SOCl2, then you get the acid chloride plus SO2 and something else. What else? Anybody? One more thing. Nothing. Okay. So you also get HCl, right? And this is a gas, and this will probably come off as a gas too. Okay. It might stay in solution, but we're not too worried about it, right? If you use oxalochloride, which I'll write like this, then you get again your acid chloride because that's what you're making, and then you also get CO2 gas and carbon monoxide gas. So, stay safe while you're doing this reaction because you make carbon monoxide, but these are the two gases that you wind up getting as a result, right? These two will not stay in solution, so they'll come right out of whatever solution you're doing this in. So that's kind of nice too. You can use oxalochloride, which should be common enough in whatever lab you're working in. All right, that covers chapter 20. So let's see, how about I save this document and I'll make a new one. New. Yeah, there we go. Okay. Now I'll make this document and we'll do chapter 21 here. Okay. So my plan is sort of to make like a bunch of these and then I'll post them all and they're images. I can turn them into PDFs or whatever. So that's sort of like what I'll do. Okay. So, okay, chapter 21. This one is acid derivatives, which is like a cool term, I guess, if you don't really want to know what you're learning about. But if you do, then there's like some list of acid derivatives or things that you can get from like acidic hydrolysis of an acid or basic hydrolysis or just like treating an acid with acid or base. So there's, let's see, like 4 or 5 or 6 or something of these. Okay, so maybe let's go through and anybody want to tell me some of them? You could use the chat or, speak and let your voice be free. Anybody? First one's easiest because,
Acid
none of
chloride.
them have been filled. What was that?
Acid chloride.
Yeah, sure. So an acid chloride. There you go. Okay. That's a good one. We've talked about it already, and this chapter is like half devoted to acid chlorides, right? There's another one that's similar to acid chloride, or at least has similar reactivity.
Anhydride.
Yeah, there we go. Yeah, so we can use an anhydride also is an acid derivative. Great. What else do we have?
Carboxylate salts.
Yeah, okay. So we have carboxylate salts. Okay, so I'll put those like down here.
Esters.
Okay, so esters can go like up here. You might notice that I'm ordering them in a kind of funky way. There's 2 more.
Amos?
Yeah, so yeah, an amide would go here, Okay, and then there's one special one that's kind of new and doesn't really come up much, but it's here. Bonus points for whoever that
And
invented
nitrile.
it. Oh, okay. Maybe I should have included nitrile. How about I put nitriles over here separately?
Bioesters?
Yeah, there we go. So thioesters are also another one. Okay. This one's like kind of new, I guess. Uh, you're not going to learn very much about them, but like they're kind of interesting, right? For those of you that are like into biochemistry, these are really important. Um, like a lot of your enzymes work by using thioesters because like one of the amino acids, like cysteine, is a thioester and or it has an sh at the end, so it's very reactive and makes a lot of thioesters. And okay, whatever. Um, this one's kind of like relevant to biology, but like we don't talk about it that much in this class, right? So there's a bunch of these, and then also nitrile. Okay, so I guess there's seven. Whoever got nitrile really showed me up. Uh, yeah, there's I guess seven of them. Um, so I ordered them in this way because if you go up, then these are going up in reactivity. Okay. And if you watch the lectures that he gave, or I'm sure he's put up this image before at some point in the class, uh, this is the reactivity series, and then there's a whole bunch of arrows that you can draw about like what goes where, and you can go like from here, and you can go up, and all that. Okay. So there's a whole bunch of these arrows that you can draw, which I'm not gonna focus on all of them because like you've seen most of these and you know how they work already. Um, this chapter is largely review with a couple of new reactions hidden in there, right? So there's a couple of new things about like nitriles, um, a couple of new ways you can use esters and amides. So we'll just kind of look at how those new reactions work, right? Okay, so let's start from the top. We're back to acid chlorides again. Uh, they're kind of inescapable because they're fairly easy to make and super, super useful. So you can go from an acid chloride to an anhydride. This is like the main way to synthesize anhydrides, um, somewhat. At least like if you were in the lab and you were doing it, this is the main way. So if you take an acid chloride and you add just the acid, then you wind up getting the anhydride. So I was looking through the book and the mechanism for this one is kind of interesting. Um, so I guess it's worth talking about for a moment. So if you have your acid here, and then I'll draw the other acid in a kind of weird way like this. So this carbonyl attacks up to here. You know, it does this whole thing and kicks off that chloride. So what you wind up getting is, oops, this will be a carbonyl, and then you'll have something that looks like that, right? And let's see, this is like a plus charge now. So you wind up moving this guy over from here, some electrons down from here, and then some water will pluck off that hydrogen. Okay, and then that'll give you your anhydride. All right, so this is kind of like a neat mechanism, I guess, um, because you have this like the O from the carbonyl attacking to another carbon, which is like kind of interesting. You've seen that this O from the carbonyl of the acid can pick up a hydrogen. Like this is what usually gets protonated, but it's interesting to see it acting as the nucleophile itself. So this is kind of one example where that does happen. Okay. Um, let's see. What other reactions have we learned? So here I mentioned earlier there's another one that's called transesterification. There esterification. Okay. So this is just if you take like some ester and then you can do it either in acid or in base, I believe. So let's just say like in acid. And instead of doing water like a normal Fischer esterification, you could do like, I don't know, methanol or something. Right? And then bam, you get a methyl ester. Right? This is an equilibrium because there's no reason you'd prefer one or the other, just besides like the actual quantities that they're present in. So this goes back and forth. Right? Not too revolutionary if you had asked me. This is totally something that you could have written the mechanism for a while back. It's just now you're seeing it and it's being given a name. So not the hugest thing. Okay. Then there's like a whole bunch of hydrolysis reactions. So you have acid and base ester hydrolysis. Okay. So for acid, you already know this one. This is like the third time I'm talking about it. This is Fischer esterification. For base, it's just attacking an ester with an OH. Okay. So here you're going from ester down to carboxylic acid. So you're going down the reactivity series. Right. So you're able to do this. This is not like a super hard reaction. Okay. You have your acid, or you have your ester, sorry. You take your OH of your hydroxide and you attack the carbonyl, right? So maybe let me just actually draw that out. That goes in there, and then you wind up kicking that ester off, right? And from there, you can handle the rest of what that looks like. Same thing for amides. What did I say up here? Hydrolysis, yeah. So acid and base amide hydrolysis. Okay. You can do the same exact conditions or the same exact like mechanism and reaction, right? Amides are lower on the reactivity series, so you need stronger conditions to do this. But like this is totally something that's possible, right? So if you really treat your amide with a lot of acid or a lot of base, then you can go from amide to acid. Again, you're still going down the reactivity series. So this is definitely something that like is still doable and possible, right? Okay. So then, nice, more hydrolysis. So you could do acid or basic nitrile hydrolysis, and this is actually one of the new ones. Okay. So, generally the way it works, which I kind of mentioned somewhat how this would work, but for let's say basic, take your OH, throw it onto there, and then those electrons will go to steal from some water. Okay. And then so on. Right. And from there, you probably wind up getting an amide, and once you have an amide, well, then you're done. You can go from an amide to an acid. So these will generally go from nitrile to amide to acid. Right? So this part you've even seen before. So it's really just going from nitrile to amide. But that's mostly just the fact that this CN triple bond is really polarized. So this carbon is like somewhat positive, and over here this nitrogen is somewhat negative. Okay, so it'll act pretty similar to what a carbonyl would because it's similarly polarized. Okay, All right, and now I'm going to throw in some of the actual like new reactions that you've learned. So if you have a nitrile, then one thing you're able to do is to reduce it. So in this case, you use dibal H, and it's got to be real cold. And from there, you could just do acidic workup, which this should wind up giving you, let's see, I believe an amide. Anyone verify that? Give an amide? Yeah, I think it does. Maybe I'll double check that it gives an amide. All right, well, how about I leave it blank and we can think about it later. So, yeah, you can reduce a nitrile, which will give you, I think, an amide, but like maybe I should just double check. Or another thing that you could do, which is like a new reaction, is if you have an amide, this is like genuinely a new reaction that you haven't seen, or maybe you have, I don't know. But if you give it POCl3, or the alternative is P2O5, then that will dehydrate the amide. So instead, then you get a nitrile. Okay, so this is dehydration. All right, this is like this is new. Maybe I'll put like a little box or something. Okay, so this is also new here. And this is good to know because now this lets you go backwards, right? Which is really helpful because that's like this is a really good way of making nitriles is to start with an amide because you know how to get to amides in a lot of cases. Okay. A little bit more so you can go. Oh, yeah, okay. So some new terms also that you learn in this section. This is really the last thing I have to say. Uh, so if you have a
I'm sorry, can you scroll up a little bit? Sorry, I wanted to see the
yes,
last one you wrote.
yep,
Thank you.
yeah, there we go.
Okay.
Something like that. Okay. So if you have, let's say, a cyclic ester, this is called a lactone. And then if you have a cyclic amide, then this is called a lactam. Okay. Um, yeah, not too much to say about these two. I mean, they'll form fairly commonly if you have like an acid and an alcohol next to each other, like on the same carbon chain, and they can form a 5 or 6 membered ring. But otherwise, I mean, they act pretty similarly to regular esters and amides. Okay. Uh, Maybe another like fun fact about lactams here, which he probably mentioned in that like recorded lecture thing. Um, but lactams like are commonly used in like biology. So a common thing is for lactams to be found in antibiotics because like you can usually wind up putting something that looks like this into like let's say not a ribosome, but I think like oh I think it is the ribosome. So like if you put something like this into a ribosome, then it kind of looks like it's supposed to be an amino acid, and then your ribosome will go and attack it, and then you can't really do anything more from there because like it doesn't have the actual functionality that an amino acid does. So this kind of like winds up breaking your ribosome or like your tRNA synthetases or whatever, some enzyme that you have going on. Okay. Um, okay. So from the chat, Julia said that nitrile and dival gives aldehyde, I believe. So that would probably make sense, I think. There we go. So I had that wrong, I guess. Um, Likely you guys have it correct. So this is probably an aldehyde, but maybe I'll still double check later. Um, just because this is like yet another one of those reactions where you kind of have to just like know what the reducing agent is, and yeah, they're very particular about like which reducing agent you use. Okay, great. So that kind of covers chapter 21. That's most of what there is for chapter 21 as well. Okay, so how about I save this document with my like free knockoff version of Photoshop, and let's make a new one. So now we'll actually start. I want to zoom. There we go. Yeah, so we can actually start working on some problems, I guess. Let me open this thing and copy and paste this thing in. So oh yeah, there we go. I got it. Okay. Um, Now I will use this thing. Oh yeah, I can even move it. Except it's a bit too big. Okay, I'm not sure if I can rescale it, but I'll just move it up onto here and then actually, okay, how about I do this instead? So now you notice that like kind of new to using this thing. Okay, there we go. I made the document wider. So copy, paste. Oh yeah, okay. Now it fits. So I'll move this up all the way to the top. And we'll start working on it. So the first question is about the Hoffman and Cope eliminations, and maybe while I was talking earlier, some of you went ahead and started looking at it. So this is from chapter 19, when you were working with amines. So this is some kind of old news, right? So we have the Hoffman and Cope eliminations, and maybe let me switch to the brush. Okay. So these are both to get rid of amines from whatever you're working with, okay? Or really, I guess, to make double bonds in the compound that you have, right? So maybe just for like the conditions, with the Hoffman elimination, what do you do? Like, what is step one? Has it been that long? No. Okay. So usually what you would do here is that you have your amine and then you give it excess methyl iodide. Okay. And methyl iodide is like a super great, I guess, electrophile, or the nitrogen that you have is a good nucleophile, and it'll get methylated a whole bunch until it becomes like a positive charge, like positively charged, okay? It'll get more methyls than it can really normally handle. So from there, maybe I will draw this whole thing out, okay? So from there, you get 3 methyls, okay? And this is positively charged. So from there, what do you give it? Anyone? Anybody?
Strong
Silver
base.
oxide and heat.
Okay, yeah, there we go. So you give it silver oxide, and then you heat it. Okay. So I guess when you give it silver oxide, you put some water in there too, and then you heat this, right? And from there, what winds up happening is that you get an OH that kind of turns this into a salt. The OH minus. And then this thing will remove a hydrogen from somewhere over to here, somewhere over there. Okay, cool. So I guess in terms of like the important things about this reaction, it's called the Hoffman elimination. So does it give the more or least substituted double bond?
Least. The least.
Oh yeah, that was some good unison. There we go. Okay. So this gives the least substituted double bond. Double. Yeah, okay. All right. My handwriting was just kind of ugly there. All right. So great. Yeah, you get the less substituted double bond from this. Right. Which is a kind of, I guess, interesting reaction. This is like a different form of. This is different from what you traditionally learn to be like a Hoffman elimination, as opposed to a Zaitsev elimination. This is like an actual named reaction now, right? Okay, so for the Cope elimination, things are a little bit different. And let's see, we have our amine first, and then we treat it with something, which is what? Anybody? So we need to get an oxygen in there somehow, right? So we want to turn, in the Cope elimination, we go from amine to amine oxide. And if you want to oxidize, what's a nice way to do it? Hydrogen peroxide is one way. Okay. So yeah, we can use hydrogen peroxide to go to an amine oxide, and then from there, heat this, and you get a double bond there. Okay. Does this one tend to give the more or less substituted double bond?
Doesn't it also give the least?
Yeah, it also gives the least substituted.
Could you also use like any one of the other oxidizing agents we talked about in chapter 20, or does it like specifically need to be hydrogen peroxide? I'm just out of curiosity.
Yeah, so my impression is that if you used other oxidizing agents, they'd probably go beyond an amine oxide. Like nitrogens will generally oxidize pretty easily. So from there, you can wind up getting like an N double bond O or something, or like you would wind up like over oxidizing the amine probably. So hydrogen peroxide is kind of nice because in this case it won't like really go too far. Whereas if you blasted the thing with like potassium permanganate, then you can expect that this wouldn't give you the right conditions to do the Cope elimination.
Cool, thanks.
Yeah. Okay. That's my impression. I know usually for doing Cope elimination, you use a fairly mild oxidizing agent. Like, I know that the book says you can also use what are they called? Peroxy acids, like the same thing as you used to do in epoxidation. So if you're making like MCPBA, you use yeah. If you're making an epoxide, you would use MCPBA. If you're doing this, you can also use like MCPBA to do it. But I guess hydrogen peroxide is kind of easier because it's fairly familiar. Okay, great. So there you go. There's the difference between the two. Okay, so Hoffman elimination will use these conditions. In this case, so it will over-methylate the nitrogen, and then you treat it with silver oxide, which makes a base, OH. And here the Cope elimination will make an amine oxide, so which looks like this. And then from there, this O minus will do the actual elimination part. Okay, great. Okay, so there's one problem that we've done. How about we switch back over to here and do the next one. Okay, let me find the question. There we go. All right, found it. And I want this thing, and I'll move it up. Okay. Cool. So this is just another review one. I kind of like having this problem, and I talked about it a whole lot before break, so some of you may remember this. Yeah, so okay, you have like some aromatic with an NO2 hanging off the end, and now you want to get rid of it and replace it with something else. So this is a fairly fast one. How would you change this NO2 into something that you can get rid of really easily?
Like some kind of metal reduction.
Let's see, reduction. So if we reduced it, I think the only thing that we can really reduce it to is this NH2. So that would be like you can use a whole bunch of different conditions, but like to be extra lazy, you could use the Clemmensen reduction conditions to do it. So you could do that, but then this is still a pretty tough thing to get off.
But can't you convert it to a diazonium group?
Yeah, okay, there we go. Yeah. So from there, you could actually convert it to a diazonium, right? Which uses like sodium nitrite and what, some acid? Yeah.
Yeah.
Is it nitric acid? I think it's nitric acid. Is it?
I have hydrochloric acid.
Oh, okay, that's a good one. Yeah. I don't think the acid winds up making a huge difference, but you use, there you go, yeah, sodium nitrite and hydrochloric acid. Okay. Yeah, and then from there, that will change this NH2 into a diazonium salt. So this thing turns into an N triple bond N plus, and now we can get rid of this thing pretty easily, right? This thing comes off without much problem. So, all right, cool. Yeah, that was kind of it. It's worth keeping this whole diazonium thing in mind because, I mean, it's super useful, right? There's like 10 reactions you can do once you're at this point, and yeah, that's a super useful and powerful way to swap things out in aromatics. You'll notice that this N triple bond end hanging off is the same thing that you have in diazomethane. So it's the same one as in uh, this diazomethane, but I guess if you're like interested or as a fun fact, diazomethane is made in a different way. So this method is used for like aromatic things, but then for diazomethane, you actually do it differently. There are like special compounds that you can use to make diazomethane that don't involve this process. I mentioned that because when I took the class, I think I remembered it being mentioned that you could do this to make diazomethane, but I wasn't able to find that anywhere online. So I don't know. If you're, if you're interested, then, well, that's something that you could do. All right. Well, oops. Let's pull some more problems. And let's do a whole bunch of these. Okay. Paste. Oh, nice, it's right there. Okay. All right, so let's start with A. And hey, this is kind of relevant because this thing here is diazomethane, right? So we were just talking about it. So here's a phenyl ring, and then we have this carboxylic acid, and we're giving it diazomethane. Okay? So what's that going to get us as the product?
Methyl ester.
Yeah, thank you. Yes, yeah, so this will give us a methyl ester, right? There we go. That's what happens when you have an acid and you treat it with diazomethane. Uh, yeah, that's kind of it. There's not a whole lot more to it. So that's kind of nice. Okay. So, all right, question B. We have this ring. Here's this OH, and there's another alcohol, and we're treating it with carbonyl chloride. Okay. Cool. So, anybody have any ideas of what will happen in this reaction? Anybody?
Is one of the alcohols gonna attack the carbon reagent?
Yeah. So, okay, so we'll get one of these alcohols to, maybe let me do this in a different color. And actually, even better, why don't I redraw this thing to show what it actually looks like? Put it in black. Here we go. Okay. So it'll attack over here, and this will come up here, go there, okay, and all right, well, it'll kick that chlorine off, right? This is just gonna do an acyl substitution, which, you know, we've seen that before. So there we go. I picked this alcohol, but maybe you could pick the other alcohol, and someone can try it at home and see how, you know, how it works and if it gives anything different. But I just picked that one, uh, kind of arbitrarily. Okay, and now we're over here, and this is kind of nice because we have an acid chloride, right? So not only do we have an acid chloride, we also have, maybe let me pick a real different color. So now we have 1, 2, 3, 4, 5, and 6 things here. Okay? And well, there's this chlorine, but from here you might be able to see what we're going to have happen, right? So since we have an acid chloride and we have an alcohol, and even better than that, they're right next to each other, we can probably expect that this alcohol is going to come over here and kick off that chlorine. And oh, there we go. Okay. So from there, we have this oxygen, we have this other oxygen, and in between, we have our carbonyl group. Okay? Cool. So what did we form?
A lactone?
So in some sense, this is a lactam or a lactone because we have an ester in a ring. But even better than that, what did we form? Oh, hold up. Okay. No, you're totally right. Okay. Uh, sorry. I was thinking we formed an anhydride. I had a total brain fart. Yeah, okay. So this is a lactone. In some sense, it's kind of even more than that because it has an oxygen on both sides. Um, but yeah, this is what our product winds up looking like. Uh, I drew my ring kind of weird, but once again, we have 1, 2, 3, 4, 5, and 6 things here. So yeah, it's a 6-membered ring. Yeah, I guess it's like some sort of a lactam. Um, and yeah, okay, this is our product. Cool. All right, how about we move to question C? So here's what this whole thing looked like. Move to question C. So now we have a phenyl ring, this carbonyl, and an acid hanging off. And oh boy. All right, I'm gonna rewrite it down here. There's a lot of scrolling involved. So here we have this phenyl ring, which I'm gonna go ahead and guess is not really involved in what's happening. And then we have this acid. All right, so step 1, we're doing sodium borohydride and ethanol. Okay, so let's see. This sodium borohydride, is it going to do anything with this acid? Yes or no?
No, because like NABH4 doesn't. It's like selective and only reduces ketones and aldehydes.
Yeah, great. Okay, so this thing only reduces ketones and aldehydes. All right, so it's not going to reduce that acid, but hey, look at that. We have a ketone over here. Okay, so for step 1, we're going to reduce that ketone. And we have this acid left over. All right, and okay, cool. Now from there, second step is that we do CH2N2, and it's an ether. Okay, cool. So now we have an acid and we're treating it with diazomethane. And, well, I've talked about it like 5 times, so maybe it wouldn't come as a surprise if that acid now turns into a methyl ester. Okay, and there we go. That is our product. Let me do it in blue now. Cool. Okay. Cool. Right, and now D, which I'm just going to draw here and not scroll up. So, all right, let's see if I can draw this. This would be a challenge to draw on the whiteboard, but now I'm doing it in a virtual environment. So this is going to be interesting. Okay, so we'll look. There we go. That's good enough. So we start off with something that looks like that, and then from there step 1, treat it with lithium aluminum hydride, and that's an ether. Okay. So let's see, what functional group are we really working with in this molecule?
An ester.
Yeah, okay. So lithium aluminum hydride plus an ester will get cleaved. Okay, so we're going to cleave the ester using this lithium aluminum hydride. And more than that, we're going to reduce the ester into some alcohols. Okay, so what I'll draw is that we cleave the ester at this location, and then plus we reduce it. Okay, so to draw that out, what our molecule winds up looking like is still this big ring, and now up here we have a carbon and an oxygen. which gets reduced. And over on the other carbon, we just have that oxygen, which becomes an alcohol. Right? And to make everybody's life a little bit easier, let's just redraw it as two wedges with alcohols. Right? And now, let's see. Step 2 was aqueous workup, so we already included that over here. And now step 3 is PCC. And chromium reagents aren't really a common thing, so how about we just say SWERN as an alternative? Okay. So let's see. We have alcohol 1 and alcohol 2. So is it going to oxidize alcohol 1? Write in the chat if you think it's going to oxidize alcohol 1. Right. Not getting a lot of responses. Think so. Okay. So, I mean, in general, if we have like some alcohol hanging off something and we do SWERN, then will this alcohol get reduced or, sorry, oxidized to a ketone? Yes. So no and a yes. Okay. So yeah, SWERN is able to do this. Okay. So if we have an alcohol, then it will always become a ketone or an aldehyde.
Whoa.
Yeah. Okay. So yeah, it definitely would be different if it was on a benzene ring. Yeah. Fortunately, we're not working with it on a benzene ring here, right? Am I? Yeah. Okay. Yeah. So yes, Julia, they do both get oxidized. Yeah. Okay. So this one here on the ring doesn't make a huge difference, so it does get oxidized. And this one over here is just a primary alcohol, so sure, yeah, it'll also get oxidized, right? So redraw our ring. This one turns into a ketone, and this other one, remember, we have a stereocenter here with a wedge, and this one turns into an aldehyde. Oops. That is like, okay, this is a real ugly aldehyde. There we go. So it looks like that. All right. And maybe if you're keeping track and you really love these sorts of problems from way back when, this is still a chiral molecule because it has this stereocenter here, but we get a racemic product. Okay. The other reactions that we did earlier might have also been racemic. I wasn't paying attention there, but this one, just for fun, yeah, this one comes out to be racemic, and we should indicate that, right? Reason being is that we have the hydrogen also sticking off here, so that means that we have 1, 2, going around the ring, 3, and then going around the ring this way, 4 different substituents. Since there are 4 different substituents on that carbons, it's a stereocenter, so yep, the molecule comes out to be chiral. Let me stay up here. Okay. Okay. Maybe before we move on, does anybody have questions before we go? Anybody? Yeah, I mean, as we're going along, you definitely like feel free to interrupt me. I have zero problem getting interrupted. Um, it breaks up the whole talking to myself alone in my room thing, so, if
Would you
anybody
mind
doesn't.
would you mind re-explaining why the product is racemic?
Yeah, so um, here we're starting with, let's see. Oh, maybe I put myself into an interesting spot. So here these carbons actually are uh, enantiomerically pure, aren't they? Because each of them has like one, two, three, and four different substituents. So maybe it actually could wind up being that this comes out enantiomerically pure. Uh, yeah. So in this case, we wind up with this guy sticking. Yeah. Okay. Yeah, that's interesting. Is that I don't know if that's what you were going for, but this actually might wind up being an enantiomerically pure. I didn't go through it all exactly,
Does
but
that mean you get only one of the enantiomers, like out of the
yeah,
reaction? Okay.
yes, I think. Huh. Okay, I've put myself into an interesting spot now. So now I have to answer my own question, uh, which is fun. Um, yeah, so let's see. We start with this, and then these things are both sticking up the same way, except all of them look like this and not the mirror image. So yeah, the mirror image would look. So this is still a chiral molecule because there's no plane of symmetry, right? So this is so we start with chiral because there are four different substituents on each of these two carbons, and then we break the ester. Yet this is still chiral. Okay. And now I just redrew it, so that means it's still chiral. And over here, it's still chiral as well. And in that process, we did not change. Let me pick a new color. We did not change this stereocenter. Okay. So here it was like that, and now it looks like that again. Okay. And it still is like that, and bam, at the end, it's still always going to be of this form. Okay. So what I think is that this actually will come out enantiomerically pure because we likely the question didn't specify, but this thing was probably enantiomerically pure when we started. Okay. Yeah, I guess I put myself in an interesting spot there because I wasn't expecting that we started with something enantiomerically pure. I didn't think about that at first. Okay. But I think that our product at the end should wind up being pure as well. Does anybody really disagree with me? Because you're welcome to. I didn't think this through beforehand, so it very well might not be an enantiomeric pure. Anyone? No? You guys are on board? Okay.
We just trust you blindly.
Oh man, that's that is a bold place to put your faith in. Uh, but well, I guess you can give it a shot. Um, yeah, maybe I. Yeah. Oh look. Oh man, I hit the bottom of the page. Oh, okay, nice. That's good. Okay. Well, I guess I'll save this then. Um, oh sweet, and we finished the whole of problem 3. Okay, yeah, this is good. All right, things are really working out well. Um, maybe while while you say that you're blindly putting your faith in me, uh, it might be a good time for me to mention that you guys are pretty close to the end of the course, meaning that uh, in a very short amount of time, you will have the same amount of organic chemistry knowledge that I do. So, uh, I don't know if that might put things into perspective for some of you, but like soon, in a pretty short amount of time, uh, you know, you will be equally qualified to do what I'm doing. So, uh, maybe that might be a nice thing to think about or reassuring or something, but give it a month or two and you'll know all the same stuff. Okay. While I'm at it, I'll also plug in the email that I sent, the first one, or like the first Canvas notification thing, there was a link to apply to become a workshop leader, which I totally recommend that some of you guys do. I've had people ask me about it before, so like if you want to do what I do, not hopefully not through an online format next time, but if you want to lead workshops yourself or something, like I really definitely encourage people to apply. Um, it's pretty worthwhile. It's fun. It's great. I get to meet all of you people, which is good. Um, and it helps you keep up on organic chemistry because Lord knows I'd forget if I wasn't responsible for teaching other people. So think about it. Okay, anyway, all right, I'm done with that. So how about we paste in some new problems from over here. Whoops. Okay. Every time I switch between the programs, it's weird because like scrolling is totally different. Okay. All right, let's copy this thing and move it over to my knockoff Photoshop. So, all right, we'll move this up. Let's see. All right, this question, as I'm, slowly inching its way up. Okay. So we are tasked in this question with proposing a plausible mechanism for this problem that we have here. Okay. So provide structures of intermediates, use arrow pushing formulas. Okay, cool. Great. So maybe if we're starting to approach this problem, then how about we take a look and we see a couple of different interesting things. So over here, we have, let me use a different color because I use green for stereochemistry. I like blue. So over here, we have an acid, which winds up going at the end to an alcohol, but we also lose that carbon. Okay, so there's some interesting stuff going on with that acid. And then over here, we also have this functional group. And does anybody remember what this functional group is called? Anyone? It's got two oxygens sticking onto the same carbon.
Inositol.
Yeah, okay, it's an acetal. Thank you. I was asking because it's been like more than a month since I even saw the terms, so, your memory might be a bit more fresh than mine. Okay, cool. So we have an acetal, right? And we're putting in an acid, and that's like the one thing that we can do with acetals is put them in acid and break them. So maybe to start, let's take our starting structure and we are putting in an acid, so here's an H3O plus. Okay. And my bet is that one of these oxygens is going to take off that is going to get protonated from that alcohol, from the acid that's floating around the solution. Okay. Do you guys think it'll matter which of the two oxygens gets protonated? Just from looking at what we're working with here?
Yeah, it has to be the one on the right closest to the carboxylic acid, right?
Okay.
I
Why
think.
do you think it's the one on the right?
Oh, I was just thinking because the ring that you have to make in the end, I thought would have to involve the one on the left in order for it to be a six-member ring.
Ah, okay. Yeah, so you think we're gonna use these oxygens will become alcohols, and then from there, this carboxylic acid and the alcohol will make an ester. Okay. I think that's what you were saying. Hopefully I interpreted that right.
Yeah.
So, okay, that's a pretty good idea. Um, sure, so let's protonate the one on the right, and we'll see what happens from there. Okay. So, whole bunch of equilibrium arrows going on because we're just protonating. Whoops. We're just protonating and deprotonating. Okay. And we want to break this acetal. So what are we gonna do with this OH plus? Or rather, what are we gonna add to this whole thing to get rid of that acetal?
Like this makes it a good leaving group now. It has the positive charge.
Yeah, so it's a good leaving group. Okay. So what's gonna come in place and attack? I've already drawn an O for. So
Water.
yeah, okay. Yeah, so I already drew the O, so yeah, water will come in, and maybe let me draw electrons in red. I do like having the different colors, though. This is honestly better than having the uh, markers in the room that we normally have workshop in, particularly because most of those markers are usually dead. But hey, you gotta look on the bright side, right? So great, we'll kick that off, and now we're left with this H2O plus over there, and we have an alcohol over here with an acid down at this end. And to my friend earlier who was saying that we wanted the alcohol to be on the left, well, oh man, we're stuck without the alcohol on the left now, which I guess is a little bit unfortunate, but that's okay because, hey, we're gonna deprotonate this water, okay, do a whole bunch of, minor housekeeping steps. Whoa, okay, okay. There are probably a bunch of keyboard shortcuts and everything for me to use in this program. I totally don't know them, so uh, I would say maybe if some of you are like Photoshop wizards, you can help me out, but at the same time, I'm not even using Photoshop, so this is truly uh, this program is actually kind of nice, but it's definitely not Photoshop. Okay, cool. So we're over here, and now we want to turn. Maybe I'll use a different color. So we want that H to be there and to remove that. Okay, so that's what we want. So what we're actually going to do is now move these electrons down and, well, okay. How about we take this oxygen and protonate it? That might be a good first step because otherwise we would. All right, I'm gonna erase this stuff because things are getting a little too confusing. So if we
How
didn't
do you know
protonate
that
it
that?
first,
Sorry. How do you
sorry.
know that group is what you want to cleave?
Yeah. So we want to get this alcohol here, and this is just like following the steps of getting rid of an acetal.
Okay.
So whenever we get rid of an acetal, we get back two alcohols and we get back a ketone as well, or an aldehyde or something. Okay. So In this case, we've gotten one alcohol back over here,
Mhm.
or maybe I'll put it down over here. So we'd expect that the other alcohol is going to show up on the same molecule. Uh, I think you'd wind up getting a really weird and kind of contorted molecule if you put the ketone and an alcohol on the same molecule and then needed another alcohol to come in from somewhere else. Actually, I'm not sure if you can even do something like that. That might get really complicated. Yeah. So you expect that this one over here will also, this alcohol over here, or sorry, this O will also want to become an alcohol. And to do that, we're going to have to get rid of that whole carbon stuff that's hanging off. We'll want to get rid of this whole thing. Okay. So let me get rid of my many distracting markings, and I'll get rid of this H2. So we want to do that cleaving, and to do that, first we're going to have to protonate this oxygen. So normal, take it off of the water. Okay. If we didn't do that, then you'll see we would have wound up getting a negative charge. And one of the common things that shows up in this course is that you can't really have negative charges in acidic solutions, or at least not like things that aren't salts. So in general, you wind up having only positive charges or neutral charges in acidic solutions. Okay, so now we have that as an OH, the plus charge, and then a whole bunch of other OHs. I count 4 OHs on this molecule, which is kind of a lot, but fortunately we're about to get rid of some. So from there, we want the alcohol to remain on this long chain and get rid of this other stuff and turn it into the ketone. So we will go ahead and start turning it into a ketone, make our alcohol there neutral, and then this stuff will go away elsewhere. So this gets like right, we get rid of it, and we're not that worried about what happens to it. It goes away, it's lost, whatever. Okay. And then we can draw what we're left with. Whoops, those are 2 forward arrows, which are not super helpful. Right? And this all was in the process of breaking an acetal, which is completely reversible. So just, remember to draw your equilibrium arrows. All right, we're left with this chain now. Okay, I can't undo for some reason. That's kind of weird. All right, whatever. Cool, we're left with this. Okay. So our structure at the end is a 6-membered ring, right? So let me scroll up. So we want from this carbonyl to be 1, 2, 3, 4, 5, and 6, where the oxygen is the 6th one, and there's an alcohol hanging off the 3rd one. Okay, so let's go back down, and okay, we know that the carbonyl is going to be number 1. That's what we chose. So then we go to 2, and this one would be number 3 if we keep going down the chain, and that's pretty good because, hey, we have that alcohol hanging off number 3, right? So then if we keep going down the chain so that this carbon is number 3, then we get 4, 5, and 6 with this alcohol at the end. Okay? Good. So what we can imagine is that we want to do an esterification with the C double bond O that was on number 1, and then the OH that was on carbon number 6. Sorry, carbon number 5. Yeah, there we go. Okay. So from there, you do Fischer esterification. All right. Do you guys want me to go through the Fischer esterification, or do you think from there you can handle it? Anybody? No? Okay. From there, I will guess that, I will leave it as an exercise. To do the Fischer esterification. Okay. So you know which ones it's between, and you've seen the mechanism for Fischer esterification before, and it's good practice because it's really one of the most common things you do in Orgo 1 and 2. So, yeah, I will leave you to do the Fischer esterification. Okay. And from there, you could see how you get this final product, right? You have this alcohol on number 3, you have this carbonyl at number 1, and this oxygen at number 6. So we have all the features that we wanted. We made an ester. We have our alcohol hanging off. So there we go. All right, that gets us our product. I guess to summarize, so first we cleaved the acetal, or maybe let me just say, we removed the acetal. And then from there, we did Fischer esterification. Okay? You've seen both of these reactions. These are old. These are familiar friends. Maybe not friends, okay? But you've seen these before. You know how they work. You've seen them. You've done them before. So you can see that the problems for this like chapter or section are fairly familiar things. The things that you've done before. It's just now you're kind of combining everything together and doing it all at once. Right? And now we'll finish off with problem 5. Oh man. Yeah, okay. Problem 5 is a real fun one. So let's copy this. Where'd it go? There it is. Okay. And where's my mouse? Okay. Cool, so we'll work on this problem 5 together. Scroll in. Okay, and I want my brush. There we go. All set. All right, let's see. Where do we even start? Cool. So we could probably start around question A or so. And all right, just want to make sure I didn't undo anything that I shouldn't have. So let's start up here. Okay. So we're starting off with this thing, which, if I'm not mistaken, is called toluene. However you spell it, toluene, I don't know. Okay. So we start with this thing. Maybe I'll just erase this so I don't embarrass myself. Okay. Great. And we do bromination on it. Okay. So this is like your usual electrophilic aromatic substitution where we're putting a bromine on. Okay. So here we get a para product and we get another product, which is what? Anybody?
Ortho.
Yeah, okay. Yeah, so we get the ortho product too. Right? And Good. How about I really zoom in now? Oh yeah, that's nice and close. Okay. So we have the para product, and let's draw in the ortho product too. I'm gonna need a smaller brush for this. Damn. Okay. So draw this in, and we'll get the ortho product that looks like that. Okay, cool. There we go. There's question A done. Now we're gonna treat it with sodium amide. Okay, and sodium amide is a very strong nucleophile. So what reaction are we gonna do here? Anybody?
SN2?
So it would be SN2 normally, but this is on an aromatic ring. So instead of SN2,
Nucleophilic aromatic substitution.
yeah. So we'll do nucleophilic aromatic substitution, okay? And this question doesn't ask for it, but something that you would like 100% totally be asked is what mechanism does it follow? There are two mechanisms, right? So one of them is just standard, like, I don't know what to call it, like displacement. And the other one is what mechanism?
Benzyne.
Yeah, so this follows benzyne. And the reason for that is because, actually, does anybody want to answer that for me?
There's no electron, like strong electron withdrawing agents on the ring, or is it the reverse?
Yeah, no, so that's exactly right.
Electron
So there's
withdrawing.
no really, yeah, sorry, okay. So there's no really strong withdrawing group, right? Hannah, was that you? That's what
Yes.
this program told me. Yeah, there we go. Okay. So there's no really strong withdrawing things on this ring. So that means that it's going to go by benzyne, okay? Because normally if there's something that's really strongly withdrawing, then that sodium amide could kind of easily just hop on there. But because there's not, you have to do benzyne instead, which like is a real pain, and you know, it's got a real nasty like mechanism or whatever, but that's the reaction that's going to happen here. So if we draw out what we wind up getting, then we'll stick that amide on there. Okay. Or amine. Yeah. We'll stick that amine on. There we go. Okay. Yeah, cool. All right, and now we've got an amine, an NH2. So this is a primary amine plus an aldehyde. Okay, so what are we going to form? Anybody?
Wait, sorry, I have a question on B. Why did we put the amine like next to the methyl instead of putting it in a para position? You might have already said that and I missed it, sorry.
Oh, I guess so. Here, when we made this brominated thing, we made para and ortho. I just assumed that we were going with the ortho thing.
Ah, okay.
Yeah. You could do the problem also if you went with the para thing, but I think everything after step one, like making product A, would be the same, just located in a different spot. Yeah. Yeah, that is a good question. The NH2 also will replace where the bromine was, not in this other position. Yeah, I think it would preferably replace where that bromine originally was, so that's why we put it here. Okay. So here we have this really good nucleophile amine, and we have this carbonyl group. So the amine will really want to go onto that carbonyl group, and this is in acidic conditions. So if you have an amine and a carbonyl, or specifically an aldehyde, in acidic conditions, you wind up getting something in particular. And maybe those of you who were at the workshop before break happened might really be irked by this. Let's say maybe that this is pH 5. That might jog anyone's memory.
Is it not an amide?
It's an imine.
Amine.
Oh, yeah, right?
Yeah.
So we'll have that still there, and then our N, and then we keep all of what's over here. Okay? So there's an H there, and bam. Everything else has stayed. Okay? Now we have sodium cyanoborohydride. Okay? This is one of our nice reducing agents. We have like a bunch of them, and this is one of them. So this reducing agent particularly is used to do which reaction? Anybody? Like, what is this reaction of making an imine and then reducing it called?
Reductive amination.
Yeah, there we go. See? You know it. Reductive amination. Know how to say it, but not spell it. There we go. So this is reductive amination. Okay. So we're just going to reduce that imine into an amine instead. So we're going to keep our ring, and if we want to reduce this N into having only single bonds, then we have to give it a hydrogen, and otherwise everything else will stay the same. So how about I count 1, 2, 3, and 4 to make my life easier. So then we have 1, 2, 3, 4. Okay. That's what we have. All right, let's keep going through the alphabet, I guess. So E now. So we have this nitrogen, this amine, I should say, set up. Okay, and now we have, oh boy, yet another ketone. Okay, and again we're using sodium cyanoborohydride. Okay, so maybe it wouldn't come as a huge surprise if I said that again we would wind up doing a reductive amination, right? So what does that look like? Well, this time they give it to us all in the same reaction, but let's break it down into steps. So first, we keep what we've got, all this stuff, okay? And now we take this part plus this amine, which will give us a double bond in place of that ketone. Okay? So the simple way to think about it is to replace the oxygen with the N. All right. So, all right, well, we'll do that, right? Replace that oxygen with the N. So double bond there. And there we go. Okay. Now that nitrogen has a positive charge, so, all right, cool. Now we can reduce it. So PH3CN. All right. We can reduce it, which just means we'll put hydrogens across that double bond. And now let's do exactly that. We'll just put hydrogens across that double bond. And there we go. That's our product. Okay? Maybe let me zoom out just a tiny bit. How do I scroll? Okay, scroll like that. Okay, so that's our process. That's what we did. Okay, are people on board?
Good.
Yeah, we good? Okay.
So does that N have a lone pair in it now, and then the hydrogen's coming off the ring, so that the N has a neutral formal charge?
Oh yeah, yeah. There we go.
So
So
the
the
H
hydrogen, yeah,
double.
you're right.
Okay.
Yeah. So the hydrogen will be coming off the ring, and this N will have a lone pair. Yeah, because the N is going to be neutral. Good point. Cool. Okay. And all right, what about this other pathway we could have done, where we would have taken what we had here, and we would have done excess methylated it, and then silver oxide and heat. Okay. So excess methyl and then silver oxide followed by heat. This is what reaction?
Hope.
Hoffman. Elimination.
Oopsies.
Hope and Hoffman. So
Hoffman.
this one is so this one's Hoffman. Yeah. Okay. So here we are doing the Hoffman elimination. And cool. So what hydrogens do we actually have to remove? Well, let's see. We've got these three. Can we make a double bond anywhere with this carbon though?
No.
No. There we go. Okay, so we can't use those. And then we've got hydrogen there, and two more over there. Okay. We've also got the ones that are on the double bond already, but we can't use those. Okay. So, okay, so we know it's probably just going to be one of these four hydrogens. Okay. Um, Maybe now I'll ask, which is a fun question. Which of the pairs of hydrogens is it going to be? Is it going to remove from one or two?
2.
Two. Yeah. Nice. Okay. So, uh, we expect that this bond here is going to go. Let's see. We're going to have something come in and remove it, right? So we have like an OH minus there. Okay. So it's going to pull one of these hydrogens. The electron pair is going to go into that bond, and then these electrons are going to go off to the nitrogen. Okay. What that means is we wind up getting two products. And fortunately, if I zoom out, there are two product boxes, right? So let's draw them as they're next to each other, or like in the order that they're already in. So one, we have this phenyl ring, and we just gave that nitrogen the electrons it wants. So there we go. It'll look like that. Okay. The other thing, we just made a double bond on the left part of it. So right there. Okay, will be a double bond, and then the rest of the molecule will stay the same. Right? There we go. We've made whatever this thing is, and then butadiene, which many of you have seen before and you might not be fond of. Right? This is what we're working with. Okay. Let's just finish up the rest of these. I guess there's an entirely separate chain of reactions. Okay, that's kind of interesting. Right, let's just finish these guys up. Okay, so we can start with this thing too, and we can nitrate it. From there, we could do metal and acid onto a nitro group on an aromatic ring. So we fortunately have seen this loads of times, and it's just a reduction of that nitro group. Okay? Great. Now we're giving it this this ketone again, and we're giving it a reducing agent. Okay? We just did this reaction. We've seen it already. So we know what's going to happen. We know it's going to form an imine and then reduce. Because this is what reductive amination is, right? So we will keep this ring, we'll keep that nitrogen there, and it's going to keep one of its hydrogens, and there we go. We just added a carbon-carbon group onto it, right? And maybe let's just double check that these two pathways come together in the right way. So we would expect that this nitrogen would attack here and pop that chlorine off, okay? And then from there, you do lithium aluminum hydride, so you reduce it, and then you do acid workup. And if you'd like, you can go through all the steps, and you'll see that you wind up getting the same product. It winds up coming to this too. Okay? So hopefully that's a bit reassuring. We did things right because, well, we either did things right or we screwed up real big twice. So the chances of one are less likely than the chances of the other. Right? Let's go to this other pathway and just wrap up. So, okay, so I guess we at least know what we're starting with. We do know we're starting with this thing because there's this plus that I didn't notice. Okay? But we don't know about what products we're actually making, so that's like not the most useful thing to know in the world. So how about instead we go over here and look at what we end with, and then we work backwards. Okay. Oh, where's my mouse? Okay, there we go. So we're starting with this compound over here, and then we do a workup on it to go back. So maybe if we want to go backwards, then we do a workup. And the only thing that there is to work up on here is that alcohol. So we know that this is going to have been an O-. And the rest is hanging off. Okay? So we had given it cyclohexanone too, and this magnesium should signal that we had some sort of Grignard there too. Okay? So the fact that we had given it cyclohexanone, oops, it's not aromatic, there we go. We gave it cyclohexanone means that we had earlier had a Grignard there. Okay? Cool, so that's good. That's something that we know. We know what we had earlier. So it was likely that. Okay? Or it was a Grignard of some sort. Maybe I should write MgX here. And some of you probably noticed why. So I will write MgX instead. Right? So here we have then what I just drew below. That. Okay? And we're going to have to look at a couple of these steps in between to try to figure out what we've actually done. So, over here, we have sodium nitrate and HCl. So you might notice that this is making an arene diazonium. Okay? And once we have a diazonium, we're adding copper iodide. So that makes diazonium into an iodide. Okay. So this MgX that I had here is actually an MgI, which is a kind of interesting Grignard reagent to use, but no harm in it. Okay. And since we went from a diazonium to an iodide, we know that over here, what we had was precisely that diazonium. Okay? And, I'll see. Okay,